Hi, I'm Petr Krysl and I use Julia for prototyping algorithms and for implementing computations in ad hoc simulations for applied science projects, for instance, hearing in marine mammals. This account is intended for researchers who are looking to Julia to boost their productivity. So by no means for Julia experts, but rather the novices. This account is not complete and I do not have supporting data. It consists mostly of personal experiences. I would like to point out that there's an organization, Julia PDE, which demonstrates that the Julia environment for solving partial differential equations is quite rich and reasonably complete, be it solvers, libraries for building simulations, or application packages. There's probably little that is missing. I came to Julia for speed. The ability to produce fast code was, and still is, prominently featured in Julia documentation. It is really nice to have a fast language that can be used to write everything. So here I show the so-called acoustic color graph, which is obtained by circling around a scatterer underwater and also sweeping through frequencies at the same time. The model is coupled finite elements and boundary elements, and it tends to be expensive. Each column in the image towards the right, that is for high frequencies, tends to take hours to complete. And I can use Julia from the Green's function microkernels through operations on big complex matrices to the overall structure of the simulation and management of the data. This is all nice, but what really impresses me these days is something else. Julia is somehow able to increase my productivity by being consistent, easy to read, and flexible. I have done some work with C++. I don't think I would have been able to complete the code without the debugger. Moving on to MATLAB, I thought that being high level, it would be a step up from C++. But somehow I still spent my days in the debugger. About 3 years ago, I committed to Julia. The other day, I realized I haven't needed the debugger once in all those years, despite having programmed some 100,000 lines of code. I had to do a mental double take when I realized that it was quite shocking. Here, you will recognize the classical example of the linear, heat conduction, bilinear and linear form evaluation from a Galerkin finite element model. With a little bit of care, one can write code that doesn't really require any explicit type annotations. The compiler can figure it out on its own. In combination with static arrays, one can get very clean and at the same time high performance code. So both fast and easy to read. But asking for performance may run into some language limitations. Take, for instance, MATLAB. While the code doesn't look very different, it is in fact quite a bit more complicated. The developers had to reorganize everything into arrays so that vectorization could be taken advantage of. Without vectorization, the performance would have been horrible. So the look of the code may on surface not be that different, but it is easy to see how a debugger might be required to make it work due to all those multi-dimensional arrays. Here's the same assembly procedure implemented in C++ in the well-known Deal2 finite element code. Note that this was supposed to be easy to read, being part of a tutorial for beginners. I think that this clearly shows that the explicit requirement of typing everything can really get in the way of understanding what's going on. Just compare the length of the codes and the amount of black ink. Here's another example, this time not my code, the Seagull geometric library in Julia on the left and the C++ on the right. Julia is not object-oriented, which in my opinion is a good thing. It leads to a different view of how to design the code. Here's an example. Some finite elements do not have the ability to evaluate the geometry. For instance, L2 elements with interior basis functions. They need a proxy, a geometry carrier, that will do that for them. In C++, the natural thing to do would be to store a reference to the geometry carrier in the data structure for each finite element. In Julia, the focus can be redirected to behavior. Simply ask the finite element who its geometry carrier is. Most finite elements would reply that they are their own geometry carriers. This is expressed in a really inexpensive way as a function that simply returns the argument. Those finite elements that do require a proxy can then override the above generic function to request assistance of a different finite element. Another habit of C++ users tends to be to view everything as objects. When building mesh libraries, everything is then an object. Because C++ objects are implemented essentially using pointers, this would then tend to use a lot more memory than necessary. For instance, even when the indexes themselves are stored as 32-bit numbers, the pointers are typically 64-bit. Julia makes it easy to think at the right level of abstraction. In the case of the mesh core library, that happens to be the incidence relation. When the incidence relation has a fixed cardinality, and the short vectors of the fixed cardinality are stored as static arrays, the compiler is then clever enough to eliminate any and all pointers and store everything in one contiguous array. Thus, for instance, storing the entire full one-level mesh hierarchy, we can use up quite a bit less memory than the next best database. Storing the up-down reduced links only between the vertices and the elements, the Julia library again consumes considerably less memory than the comparable databases in C++. Saving on memory is great, but designing at the right level of abstraction also has the advantage of providing the user with a choice which topological relations to store. There's no need to decide beforehand what needs to be stored and encode it in the types that needs to be compiled into a library. These decisions are easy to make on the fly in the Julia design. As you can probably guess, the answer is no. There's definitely more that I like about Julia. Here are a few more things. I find the test-driven development very well supported. That and the continuous integration really help streamline development of packages. Documentation in Julia is so easy that even casual packages tend to have decent documentation. Parallel processing, be it with processes or with threads, is definitely a breeze compared to what I was used to from my C language programs. And there are other things that make using Julia for numerical computing worthwhile. Recently started experimenting with automatic differentiation for constitutive equations. Here are the references. Find tools may be useful if you're interested in prepackaged functionality. It has, for instance, high-performance finite elements for solid mechanics. Mesh Tutor might be useful if you're interested in the mesh database I mentioned in this talk. Elfel is a library of building blocks for mixed finite element methods. The intent was to write it in a way that could deliver both on legibility and high performance. Finally, the Julia PDE organization site may help you find the packages or functionality you're interested in.
Hi, thank you for having me in this session. My talk is called BEAST, Boundary Element Analysis and Simulation Toolkit. My name is Kristof and I'm a researcher at the TU Delft. So the type of problems that my package addresses is a scattering problem. Now there are scattering problems in all kinds of branches of physics, acoustics, statics, electromagnetics, elastodynamics. I will focus on the electromagnetics case because that is where my background lies, and that is also the area in which BEAST is the most matured. So we're having an incident electromagnetic wave that hits a very good conductor, a perfect conductor. And we are tasked with finding the total electric field, that is the solution of Maxwell's equations, and such that the radiated field is radiating away from the scatterer, as you would expect. And the boundary condition of this boundary value problem is that the tangential electric field on the scatterer is zero. This is the physical condition near a very good conductor. Yes. Now, these kind of problems, like boundary value problems in enclosed areas, can be dealt with by the finite element method. We, in this particular scenario, opt for a boundary element method because it offers some advantages. The solution we get is perfectly radiating. There are no approximating boundary conditions. There is no dispersion error because the solution is expressed explicitly in terms of the Green's function. This is also why the solution away from the boundary is perfectly analytic. And if you combine these schemes with a matrix compression algorithm, you even get asymptotically lower computational complexity, even though these methods are very difficult to actually implement. The mathematical description is done by reducing the boundary value problem to the boundary of the domain, and then you end up with an integral equation that is phrased in terms of the induced current J, which is also the boundary value, the tangential boundary value of the magnetic field, n cross H, on the surface gamma of the scatter, of the obstacle from which your wave scatters away. So you are looking, in essence, for that induced current, such that the corresponding radiated electric field, which is the left-hand side of this equation, exactly cancels the incident right-hand side, the incident electric field, which we choose, and, for example, could be a plane wave. To solve this system, we apply, in essence, the same technique as we do in the finite element method. That is, we move to a variational formulation. This is done by testing the equation with a generic function k. This is pretty generic apart from some smoothness conditions. And testing means that we multiply and then integrate. And integration by parts is typically applied to lower the singularity of the integrals encountered and also to give the formula a more symmetric view. And then to discretize the system, the function k is limited to a finite dimensional space, and also the candidate solution is limited to a finite dimensional space, which we here generically denote x. The package BEAST is essentially made to facilitate this process, and its design goals are that it's high performant with performance compatible to C++, easy to use in the sense that the formulation should be close to those as encountered in a mathematical description of the scattering problem. The package is easy to maintain, extend, typically by overriding or extending methods that are defined inside of the package, and easy to teach and enable collaboration, well, both with students and other researchers. BEAST is the top layer of a cluster of packages that each have a certain responsibility in this ecosystem. The main other package that it relies on is CompScience Meshes, which is a meshing library, but the meshing library is specifically aimed at computational science meshes. At the time of writing, I saw there were some excellent meshing libraries available, mostly focusing on graphical applications. And because, and I will go a little bit deeper into this, the main difference between the finite element method and the boundary element method is the level of challenge of the integrals encountered. There are some packages especially designed to deal with highly specialized integrals. One is a Zouters-Fab quadrature, and that is a quadrature method, a package that implements a quadrature method that is very general in the sense that it can deal with weakly singular and even Cauchy singular integrands on both flat faceted and curved domains, triangular and cyclical domains. Then Wilton INS 84 is a highly specialized package designed to deal with exactly one type of integrals, and that is integrals where the integrand is a power of the distance, the distance between of the radius, the distance between 2 points. And the domain is the intersection of a triangle and a spherical shell, and it will become clearer later why these type of integrals are so important in the context of boundary element methods. And BEAST ties all of this together. It contains the local and global description of finite element spaces, the operators, and it links the various geometrical configurations to quadrature strategies. To give you an idea how the package is used, this is the proverbial hello world, which actually implements and solves the problem that I talked about, the scattering of a wave by a perfect conductor. So typically you create a mesh. The mesh is, like in many other cases, a type wrapper around a vertex array and an index array. It comes with a rich API that can deal with all the issues that one would typically, all the challenges that one would typically encounter in the context of boundary element methods. On top or subordinate to this mesh, one can define finite element spaces, which are spaces of functions that are based on continuity conditions, and that when restricted to a single, for example, triangle of the mesh, have a rather simple polynomial content. The left-hand side in our formulations are integral operators for acoustics and Maxwell problems. The two basic integral operations, the single layer and the double layer, are predefined in the package. And the right-hand side is a known field, and also for these two types of physics, plane waves are implemented for both. The difference is that the electromagnetic plane wave has a polarization, which does not make sense for a pressure wave. The actual writing down of the variational problem happens in terms of generic trial and testing vectors, which you can declare, and by linking them with the finite element spaces, with the element sign, which is translated in this macro to a pair and then stored in the dictionary for later lookup. But it makes it look a little bit closer to the mathematical problem. And then these descriptions can be solved, and solved means assembled and solved by various solvers. The two main solvers that are implemented right now are a simple LU solver and a GMS solver. But I hope to expand in this area of the package. The result is actually a vector of coefficients. And in order to get something meaningful from this, you typically want to do some post-processing. The simplest form of post-processing is to interpolate the functions in the centers of the facets that make up the mesh. And then you can make a plot like this, and a plot of the norm with a color scale gives you an idea of where the current is induced, and you can see the effects of polarization. For example, the plane wave was coming from the bottom of the screen here. Other things that one might be interested in are the field in the vicinity of the scatter, for example, to examine where the energy density of energy deposited is the highest, and the far field, very far away, a limiting case, very far away from the object. And in electrical engineering, for obvious reasons, this is sometimes referred to as the rate of cross-section. Because of the field very far away from the object is high, then these objects in that direction are very visible on radar. And then you can, using plots, several Heian plots, to make various pictures of these secondary quantities. Here you can see, for example, the far field along an arc, a meridian arc, going from 0, North Pole, to pi, South Pole. And the near field both as a heat map and a contour plot in the vicinity of the object. And you can see that the contours are detached from the object, which is typical for a radiating solution, one that carries energy away from the scatter. There are various assembly-like methods that are a little bit different from the main assembly code, but are specialized to do this post-processing, and that have a pretty straightforward usage pattern. The core of the package is the assembly loop, and probably many of you know assembly of finite element methods, so I will mostly stress here the difference between finite element assembly and boundary element assembly. Boundary element operators are integral operators, not differential operators. Integral operators that are based on the Green's function and that have any 2 points in space communicate. And the consequence for assembly of this is that the matrix that will be assembled is a dense matrix, and the number of for loops in the assemble routine essentially doubles. We're not having a single geometric loop, but a double geometric loop. The role of assembly data is similar as in finite elements. So in finite elements and boundary elements, a basis function has contributions from a small number of often adjacent geometric entities. And the assembly data gives you, in a sense, the transposed information. Given a geometric entity, it tells you which basis functions are relevant to that geometric element. Quadrature data is computed before the double for loop because it will be used over and over again. So it makes sense to compute it here before. And the most important difference here is that based on the geometric configuration, the relative position of the two geometric elements under consideration, you select a quadrature rule. And the type of quadrature rule is encoded in the type of the object strat. And then you call the routine that is responsible for the computation of all local integrals, which then will be scattered based on the assembly data in the main global matrix. Now, this is actually real dynamic dispatch, but fortunately we don't suffer in performance. So the compiler optimizations are strong enough here to give us the desired performance. There is a limited amount of parallelism in this code. We're not using coloring schemes, which are a way of doing a log-free multi-threading in finite elements. The reason why I'm not doing coloring-based schemes here is that the generality of the finite element spaces that I ambition to support goes beyond the typical finite element spaces where the supports are, for example, all triangles around the vertex or all triangles that share an edge or something like that. And coloring schemes rely on this connection between topology and function definition. So rather, I order all degrees of freedom along a space-filling curve, and then I subdividing in different groups. And because they were ordered along space-filling curves, their joint domains are fairly regular shapes in the sense that their boundary is small in a sense compared to their interior. And this allows us to simply divide degrees of freedom over multiple threads. Some work that relates to geometry near the boundary will be done double, will be done twice, so you'll lose a little bit of performance. But because you patch them together using this space-filling curve concept, that overhead is not too bad, and you still get a decent speed up, as you can see here. You get a speed of 3 using 4 cores, which is not amazing, but still worth the effort with a slightly more general scheme, I would say. One thing that I think is unique to BEAST is the support of retarded potential integral equations. These are time domain boundary integral equations. And the idea is the same, but now everything has to hold for all time. So you're looking for an induced current such that the radiated field cancels exactly an incident field of your choice everywhere on the surface, but also at all times. And you can see that the retarded time, t minus the distance, features prominently here in this integral equation. It requires its own special assembly routine, which is fairly complicated, and the time dimension is dealt with differently than the spatial dimensions. There's also a relationship between space indices and time indices. The only time indices that are active, that receive non-zero contributions, are those that correspond to times that are exactly the time that the signal needs to travel between a pair of geometric entities. But the use of these methods is almost the same. The main difference now is that your finite element spaces are defined to be the tensorial products of a spatial component and a temporal component. But from the user's point of view, this is really all you need. And integrals are done really accurately using Wilton INS84 because these methods are notorious to get stable, so to get useful results out that do not explode as simulated time continues. And it's very, very important to use the highest accuracy quadrature routines, and that's why there is a dedicated package for it. The result, if you fix the point and you follow time, is this type of current that you see simulate and fluctuate and then go to zero again as energy is radiated into the space surrounding the object. Some other features that we'll quickly go through before I will go to the conclusion slide is that local operators also appear in boundary element methods. So finite element assembly is part of BEAST, and you can define quite a lot of fairly complicated also finite element problems here. For example, this is an eigenmode of the Laplacian defined on the toroidal object. It is also possible to write down systems of equations. What you need to do is you have to declare multiple trial symbols and test symbols, and then the different blocks that fit into this macro system will simply be communicated to the system by having various bilinear forms act on different pairs of trial vectors and spatial vectors. And the assembly routine will figure all of that out and will make sure that the correct contributions end up in the correct location. This is, for example, important if you want to do scattering by penetrable objects where both Cauchy data have a role to play. If you have a domain decomposition method where the equation is fixed, but the geometric configuration changes, then you can rely on a different feature of BEAST, which is the definition of finite element spaces as direct products of more atomic finite element spaces. And that is something that is demonstrated here. This is the case of multiple sheets that meet along a junction. In the equation, there is a term that acts as an interior penalty, and that will ensure that the current there fulfills the Dirichlet condition. The sum of all incoming fluxes will add up to zero. The formulation is the same. We defined the finite element space as the product of three others, and that can easily be adapted if you are dealing with different geometries of the same type. So that is where I would like to wrap up. What things do I think need to go still in BEAST? Matrix compression, speed up, parallelization, so the high performance computing stuff. Support for something else than acoustics and electromagnetics. So I would like to put static kernels in there in 2D, 3D, also elastodynamic kernels. The support for systems of equations can be better, especially in the time domain. And I would like to come up with some generic algorithm that, given a very complex geometry, will know how to put it together and then come up with a system, and that will solve that multi-domain problem for you. Integration into the existing ecosystems, there's obviously a lot of really great packages. It would be good to link to that in order to avoid any double work or to rely on features that are existing there and that are missing in BEAST. And documentation and tutorials to make it easier for people to use this package and to explain what the features are. Thank you for your attention, and if you have any questions on the chat, please let me know, or I'm also available by email. Thank you. Bye.
Welcome to Multilinear Grassmann.jl Element Assembly, Foundation for Discrete Manifolds with Adapode.jl. The Universal Exterior Algebra Foundation of Grassmann is used to devise an expressive and performance-oriented language for discrete differential geometric algebra with Grassmann elements. This is based on the abstract tangent vector space type operation at compile time. This builds a differential geometric algebra on a discrete manifold. Thanks to the Julia language multiple dispatch, there's a polymorphism based on the tensor algebra abstract type system. Recalling from the previous JuliaCon presentation, the Grassmann's duality and the Hodge complement, which is defined as an operation which takes us from a grade P to a n-p submanifold. This operation, which is a complement together with the exterior and the regressive product, satisfy De Morgan's law analog, and they also help us define the boundary operator, which satisfies the Poincaré lemma. Together, this interior product and the exterior differential combined make a Dirac operator with a Hodge decomposition. Now this is part of the interest in using this as the foundation. Now let us explore dyadic tensors and volumes of nested Grassmann elements. Let V1, V2, and V3 be given by the R3 space. From this we now construct three additional points, P0, P1, and P2, which can be thought of as a triangle in a plane. These 3 points together can be taken as an exterior product P0, 1, 2, which is equivalent to V1, 2, 3, the pseudo-scalar of the original space, a trivector. However, if we consider the bracket of P0, 1, 2, what we mean is the dyadic tensor, and this is a linear combination which is a nested sum, which is a vector of a vector, so a vector having vector coefficients. This is a dyadic tensor. Now suppose we subtract the base point to get a vector frame out of this dyadic tensor. There are actually three choices to be made. You could, for a triangle of base point, and each one of the resulting bivector volumes that can be obtained from the vector frame is part of an area equivalence class of any triangle. Now if we take the Hodge dual of this bivector and take the norm of that, we get the scalar value of the volume equivalence class. In the following example, we generalize the single triangle example to a set of triangles by extending the number of points. This is a Grassmann element mesh bundle example for the icosahedron with 12 points, which are obtained from the cyclic permutation of 0, 1, and the golden ratio, of which there are different signed variants. Together, these points provide the convex hull of the icosahedron, of which we take the boundary trivector. Here we have the 12 points obtained from the cyclic permutation of 0, 1, and the golden ratio, which we can apply a Mackey scatter plot on the set of points to help with the visualization. Next, we assign to T the mini Q hull Delaunay tetrahedrals obtained from those set of points. From this value T, we can obtain the matrix of the incidence relations as well as the matrix of the adjacency relation of T. Additionally, we obtain the boundary of T as a trivector of the 12-point space. We can use Mackey as a wireframe plot, and it automatically finds all the edges between each simplex on the mesh. We now calculate the volumes of all the edges on the boundary of T, which is help us to verify explicitly the calculations we are about to follow. The average is indeed 2.0, which is the length of the edge on each triangle. Now we take the volumes of all the elements in T to calculate the volume of the icosahedron. We sum them all up and we get 17.45. Now if we use the explicit calculation of the volume in terms of the edge length, it also gives us the same exact value, 17.45, which verifies the volume calculation. Now if we use the det simplex method on the boundary of T, we get all of the quaternions, which are the bivector elements describing each triangle. And if we take the dual of the absolute value and sum them all up, we get the surface area of the icosahedron, which, if we take the sum of the volumes of all the elements, is the same thing. And we can also explicitly calculate it using the formula in terms of the edge length and get the exact same value without any error. Given a dyadic tensor product equation in which we want to solve for x, we can do so explicitly. This means that using only exterior products, we can efficiently solve the linear system by allocating an ascending exterior product and a descending exterior product, and then taking the exterior products of them with P0. This was found to be very efficient in the Julia language, because the exterior products are statically allocated. And the comparison was made with the static arrays matrix implementation, and it was found that the exterior product method was twice as fast as the matrix one for a 5-dimensional simplex. Similarly, to determine whether a point P0 is contained inside of the simplex, it is sufficient to check the orientation of all the same exterior products as was allocated above, while the inverse requires allocating the full dyadic result. So checking whether the point is contained inside of the simplex actually requires no extra allocation. It only requires a Boolean check to be allocated. But all the same exterior products can be used in all three of these calculations. And of course, the last one can be used to obtain the hat gradient of a simplex in any dimension by only using exterior products. When we recall our set of tetrahedra T and we wish to recall the set of points, we can use the points method. And of course we can use traditional indexing to obtain individual elements. And we can actually input a tetrahedral element into the points index to get a dyadic tensor. And we can apply the exterior product to the entire set of elements. As discussed previously, the bivector volumes correspond to each triangle, and they have a complement which is a surface normal. Each of the green arrows represents a triangle surface normal, while the red arrows are the node quadrature interpolation obtained from the degree-weighted incidence relation of the surface trivector. Incidence relations can be applied using a matrix-free representation or a matrix representation. The matrix-free representation avoids the extra allocation associated with the matrix, so it can be useful to use either one depending on the problem. Here we have an example of how the Poisson equation, the transport, and the streamlined diffusion can be solved in any dimension using a unified syntax in terms of the adapode functional syntax on bundles and Grassmann elements. Nonlinear problems or time-dependent problems can be assembled by using a similar modular syntax with additional loops, variables, and boundary conditions built in for customization. This adapode functional syntax approach represents a way you can entirely rely on using Grassmann exterior algebra at the local element level while constructing a large matrix linear representation on the global assembly. This helps unify the approach of using Grassmann exterior algebra for local calculations and the traditional linear algebra packages used for finite element calculations. The following are examples of partial differential equation solutions which can be visualized with Mackie. The first one is an electromagnetic wave scattering which is interpolated from the Nedelik edges, which is all entirely done with Grassmann elements. And the second one is a 3D potential flow around the sphere. And we can also have the error residuals around the airfoil below, which can be used for mesh refinement. And we also have a transonic shockwave used from a viscous approximation of the Navier-Stokes equation. Grassmann algebra is a unifying mathematical foundation. It helps improve efficiency of multidisciplinary research using geometric tensor calculus by relying on universal mathematical principles, which include antisymmetric tensor products and geometric algebra, rotational algebras, and Lie bivector groups with exponential, conformal geometric algebra with the Minkowski plane, mixed symmetry algebra with Leibniz automatic differentiation, Hodge and de Rham cohomology with differential and contraction, Betti numbers and the Euler characteristic, Dirac and Clifford product, and the Hodge Laplacian. And now we have mesh compatibility that allows import from various other packages, including Geometry Basics, Mini-QHull, Triangulate, TETGen, MATLAB. And we can view the repository and read the documentation for details. The following are the references that can be used for geometric algebra and differential geometry, and you may want to have a look at the previous Julia Kahn talk as well.